For this next problem, I want to analyze the limit after determining the continuity of the functions involved. So I've decided to break up my function into two pieces because those are the functions involved, right? So I've got this part over here, which I'll call g of x, and this part over here, which I'll call h of x. And that makes the overall function f of x, right? Where f of x is this entire big thing, right? F of x is all of it. Oops, sorry. There we go. Okay, so we want to kind of consider each one of these graphs and each one of these functions. So let's start with the easy one, h of x. So h of x, which is equal to the arctangent of x, is actually continuous for all real numbers. It might have been a while since you have seen this function, so I'll just remind you of what it looks like. Let me pull up Desmos real quick. I'm going to turn off my function so you don't have to see that. And let me just zoom out for a second and put in h of x, which is the arctangent of x. This is the arctangent of x. This is what it looks like. You take the tangent of x and you since it's the arctangent, you flip it on its side, and you only take one outcome. So tangent of x looks like this, right? So instead of looking at all of those, you take only one of them, the one in the center, and you flip it across the line y equals x. It's an inverse, right? Okay, so that is continuous everywhere. So it's not like tangent or secant. So it's continuous for all real numbers. But then we want to consider the other functions. Let me turn off that one and look at this one. So the natural log of x to the 1/6 power. Now the thing about the natural log of x is the natural log of x is only really good for us for where the natural log is greater than, or excuse me, x is greater than 0. So let me go back here. So when I look at g of x, I know that I need the natural log to be greater, or excuse me, x to be greater than 0. But I also need the natural log to be greater than 0 because of the 6th root part. The fact that this is an even root. So I know that I'm not allowed to put in anything below 0 anyway, right? 0 and below would be bad because I can't take the log of 0 or anything less than that. So let me just mention that. So because of the natural log of x, x must be greater than 0, right? Because we cannot take the log, because we cannot take the log of a negative or the log of 0, right? Okay, so let me just, actually I'm going to get rid of the because of right there. Just say natural log of x gives us that part. Now the 6th root of the natural log of x, the thing about a 6th root is that this number in here has to be greater than or equal to 0. So since the 6th root, then I know that the natural log of x has got to be greater than or equal to 0. Because the lowest I can go is the 6th root of 0, and the 6th root of 0 is 0. Okay, well I can't take the log of 0, but I can have the log equal to 0. That's possible. So what I would do for this is solve both sides. So I would exponentiate both sides. So e to the and e to the. So that would get me e to the natural log of x, but those are inverses of each other. So that's just x is greater than or equal to e to the 0, which means x is greater than or equal to 1. So the arctangent gave me no restrictions, but this natural log gave me x is greater than or equal to, or excuse me, greater than 0, but then the 6th root part gave me that x was greater than or equal to 1, and I can't go any lower than that. Okay, so that's why when I graph this, it's going to start at 1 and kind of move its way over. So I know that the function is continuous everywhere past 1, right, from 1 to infinity. And I can tell it's continuous at 1 when I look at the graph, because when I'm going in for x is equal to 1 right here, I'm heading towards the f of 1 value. Right? If I put 1 into this function, I would get, well, here I can show it to you. So let me just mention that right here. and let me go give it to you. So the reason it's at 1 is because if I take the sixth root of the natural log of 1 plus the arctangent of 1, well, the natural log of 1 is 0, so that's the sixth root of 0 plus the arctangent of 1 on the unit circle. You're trying to think about what angle would get you a tangent of 1. So the sine and the cosine have to be the same, which would be pi over 4, right? Because pi over 4 has square root of 2 over 2, square root of 2 over 2 in the cosine and the sine. And so when you take the tangent, it's the same number divided by itself. Therefore, it's got to be the angle, which is pi over 4, that creates that. But the sixth root of 0 is 0, so this is just pi over 4. But that's exactly where my function's heading towards. I'm heading towards pi over 4. So this function value is pi over 4 over here. And if you don't believe me, I can pull it up in Desmos right here. Let me turn off the pieces and actually turn back on the function. And you can see we're heading right in there to 1 pi over 4. Actually made it a point just so you could see it, but it would go there no matter what. So it's heading to that f of 4 value, or excuse me, f of 1 value. So it is continuous on 1 to infinity. Okay, so the equation, the problem asked us to determine the continuity of the function, we did, and to analyze the limit. Okay, well, I've determined the continuity of the function, and I was just analyzing the limit kind of right here. That the limit as x goes to 1 from the positive side is equal to, of f of x, is equal to pi over 4. And we just figured that out as well, right, using the same logic. All right. Now, oh, and just for the record, there is no limit as x goes to 1 from the negative side because there's no function over here. It's not defined because you can't take the log of, well, you can't take the log of 0, you can't take the log of a negative, and you also can't take the sixth root of a negative. So all of that is out. All right, next, for example 7, we want to determine the intervals of continuity for the following function. So you'll notice there's dots on the ends here, and you don't see a dot right here near the 3's. And that means that this is an arrow. I can't draw them with my computer program, but they're there. So assume when you see that it's an arrow unless you see a nice dot, either solid or open dot. Okay, so where's this function continuous? So if I was drawing it, I could start here and draw all this way without having to lift my pen. Once I lift my pen, that's a point of discontinuity. So it's continuous from 0 all the way up until 2. And 2 gets a closed bracket because I can actually get towards 2. So I can let my pen go in towards 2 and there's a closed dot there. So I can actually head there. I'm going to join that with the next section. Okay, but the next section starts in an open circle, so I don't actually get to reach that point, which is good because otherwise it wouldn't pass the vertical line test. It wouldn't be a function. But that means that this 2 has to have a parentheses because I don't actually get to be approach to x equals 2 from that side and go to the same place that I was going here. So that's no good to me. Since I'm going to 4 and it's an open circle, I get a parentheses. And then I join that up to 3. But again, I never get to get there, so I have to give it a parentheses, right? So an asymptote or an open circle like that, I'm going to have to do parentheses. And then I'm going to join that up with from 3 to 4. But again, open circle and an asymptote, so they're both going to be in parentheses. And then from 4 to 5, but I actually get to reach f of 5, so with a closed dot. So that's going to be 4 with a parentheses because there's an open dot there. Ignore that dot because that doesn't count because I'd still have to go over here to draw this. This isn't talking about limits or function values. It's talking about the continuity. So I'd put my pen down and I would draw this whole way and then I'd put a big circle there. So that gets me 5 with a bracket. And I'm done. Those are the intervals for which it's continuous. Closed interval, open interval, and then open on one side but closed on the other.